Okay, so it's being recorded, I mean, at least on the live stream. Let me call. Yeah, Diganta will be here. He's there. So except for somebody ordering thing, so the thing that is of importance is, yeah, we will discuss your project and the concerns and your status, what the technical problems that you're having threadbare, today. The other thing is, of course, there are some reading of proof material, etc., that I've given you. Which I've asked you to start presenting. I mean, how are you making progress on that?
Yes, sir. So for that, I am done with mine. Like I just have to write some of the slides up, but I think otherwise I've understood the paper and I can explain it. So
yeah, but I need to get, we need to get, I think, who's doing what.
So I'm doing topic 1 actually. We did that.
Yeah, and
I'm doing topic 1, Debjit is doing topic 2, and Harsh is doing topic 3.
Yeah. Okay. Sorry. Okay. Fine.
So I'll be ready to present it by Friday. No problem.
Oh, good. So at least there are no concerns there, correct?
Yeah. There are no concerns there.
Yeah. Now we'll just have to agree on a time on Friday. Okay. Notice that what I have scheduled 2 days. Okay. I want your thing to plan for maybe 45 minutes, including question and answer. Okay. But still I'm devoting 2 days. So what we thought we could do was to have topic 1, and if topic 1 is done, we'll start to topic 2. And if we need to continue some part of topic 2 to the second day, it should be okay. So 2, 1 hour, 15-minute presentation time slots for 3 presentations. Okay. So I'm assuming, 45 to 50 minutes, maybe, because usually gets extended. You plan for your presentation to be about 45 minutes. Yeah.
Yeah. Okay.
Yeah. So you're okay with 17th and 24th. Is that okay?
Yeah, it works for me.
That is okay. Okay. So the rest are, flexible, but I think with priority, like you said, to give to, making sure that you are making progress and or at least trying to understand what kind of technical issues you're having, there. Okay. So do you want to?
Yeah, so I can start with some of the issues. So basically,
let me, before we get to the how you specify properties is one thing. Okay. One, you have you have run the system, that the code that Diganta has given.
And I didn't train it, but I loaded the data and I put some trial inputs and is giving outputs and all. So the LSTM is working for me.
Yeah, I
But-
think you should do a little,
Okay.
all of you should do a little bit more than that. Even before you start, this is my own personal feedback. So when I do, even before understanding what properties to specify, maybe you have some idea of the property, and then you can actually get a clearer idea of what the property is by actually running your inputs and outputs. Okay, for example, if I'll take a simple example, binary search algorithm. Okay, when if you have binary search algorithm, there are certain input constraints. If my array is sorted, and then if I'm searching to see if a particular element exists inside the array or not, then my property that I should verify is, if the element is inside the array, then my output, assuming that my array is sorted, input is sorted, and if the element X that I'm searching for in the array exists inside the array, then it should return the smallest index or an AND index of the array at which X is stored. Okay, so if this is the property that you have in mind, how exactly you specify it formally is one thing. But to, maybe you can run my program. First, I will do testing of that program to see if it works or not, and maybe there are certain assumptions that you need to understand a bit better. So after having proposed some properties that you might have in mind, I want to run the system to see on specific inputs and observe its outputs to see if my property that I'm trying to specify is indeed holds or not. So that way, that exercise can help you in not only refining or tweaking your property to get it get it to a point where you trust that property is worth verifying, and also maybe certain input assumptions, etc. Okay, that you might have to make, under which the property might be true, and assumptions. If those assumptions are not true, maybe the property is not true at all. Now, in your case, because there are certain the robustness properties, and the first two classes of properties are more cyclic kind of properties, and so on. Now, I want you to test your system on various inputs, maybe like half a dozen to a dozen inputs, and to see if those things are true for it, or you can come up with certain variations of properties within that class. Have you done that exercise?
Yes, sir. So to some extent, I have run multiple inputs and checked these conditions, whether they hold.
Okay, that's good. Okay. So then for what class of properties have you done that? There were three kinds of properties. Diganta, if I allow you, so since there are no more questions on this, I'm going to stop sharing, and I'm going to make Diganta. I want you to put that slide.
Yeah.
Which had the three kinds of properties.
Yeah.
So if you're staring at some slide, that will provoke, initiate some discussions. Okay, while he's bringing that thing up, have you, another thing that I want you to try is, besides training and running the thing and then seeing its outputs and so on, and checking its accuracy and these kinds of things, have you done something to model it? You have to input that thing into Reluplex, the Marabou system, correct?
Sir, so how are we supposed to use Reluplex here? Because Reluplex is for uh, Relu, right? So we are in this thing we have
Yeah.
sigmoid.
Okay.
and
Okay. So let
tangent.
me get back. Okay. So maybe it's not. Okay. So this is where. Okay. So so then. Okay. Then it comes the question. So if you're not using Reluplex, you could be doing SMT. So I will. Yeah. I mean, there might be certain restrictions that you can do with these systems where you can do a Reluplex. Okay, what you do is one thing. So let me raise this question: how would you, if you cannot use Reluplex because it has various Stanich and those kinds of things? How would you do it? Okay, you could directly express these things as say if I allowed you to express it in SMT logic, okay, with you use nonlinear real arithmetic. Can you express?
So in Z3, I think it's possible, sir. So I tried doing
okay.
that star product. So that was the main issue, right? So that was what was non-linear.
That is right.
Yeah.
So
Yeah. So that
so
was
the first thing is that you could do is, so have you tried to do that?
Yes,
Okay.
sir. So I tried it with some toy examples. So for those, it was able to give a solution. So I haven't tried it on a large set, but
What
Yeah,
would be useful for you to present what was the toy example that you did for which it worked, okay? And you you know, so what were the kind of examples that you did?
no, I mean, I just like basically if you want a cross product, right? So x1 y1 plus x2
so what you
y2
did
plus
was you did not take a particular DNN, but rather some nonlinear real arithmetic expressions, and try to check some properties. So try to check some
whether basically
lemmas.
to check whether Z3 can solve it, can solve
what
those.
is it that you, what are the formula that you input? What is it that you check?
No, so basically in the LSTM we have that we have those I star into I think
Correct.
I star G and those. So to encode those, basically I didn't do anything great. I just did the X, and you take X1, X2, X3 and Y1, Y2, Y3, and you put some constraints on put some constraints on them and give some value for X1 plus X1, Y1 plus X2, Y2 plus X3, Y3 and check whether Z3 is able to solve this basically. So this is the kind of nonlinear thing that will be there in the LSTM. So Z3 was able to give an output. So hopefully even when I encode the actual LSTM, it should be able to give an output.
Yeah, what I would do, the next thing that I would do is maybe make a very artificial, like, simple, one layer, hidden layer input output, and then do the same kind of activation functions, etc. That need non-linearity, because you also have to generate a formula corresponding to a particular DNN. In this case, the actual DNN that Diganta has given you, right?
Wait, can you repeat that? I didn't.
No. How are you going to verify this particular system? You will have to encode the entire DNN.
Yeah,
as
so that is
an SMT formula.
Yeah. So that is one of the main issues. So I don't know how to get around unrolling. So
no. So what I'm saying is,
so one time step we can encode it into a Z3 thing.
Now how would you start doing it? See, if you get stuck in, if you want to do, I'm taking a step-by-step approach that you could do. Okay, you could take the RNN that Madhukar showed. This is a very simple example. Have you tried doing that with the Z3? Now you could enhance that. Put some of the complexities that you will say, either you try to do the whole thing once, get stuck, and then hit a roadblock, or take a simple, start with, either have a scaled down version of what Diganta has given you, and or another way is to take a Madhukar's example, add a few things to it that gives the some of the aspects like what he has shown here in this Diganta slide, and unroll it once or twice, okay, and then check.
But so the point is that if we are allowed to unroll the net LSTM to get, suppose if the length of the input is only like 4 or something, then we can kind of unroll it, and then I don't think it should be a problem to verify.
No, I understand that. Okay, so, but have you even done that? Okay, if you could unroll and you modeled it as a, so you are confident that if you unrolled it, you'll be able to verify it, huh?
Yes, sir, I think so, because we did a similar thing for our assignment 2 also. So
okay. No, so, but okay, good. So then, what is it that? Okay, so then the other question I have is the size might be an issue. Okay, so what we were discussing was there are certain non-linearity in there. Maybe you could exactly model this. Have you modeled exactly this box, the green box that is being shown here?
No, sir, I haven't exactly modeled it yet because I was just thinking about it. I haven't coded it yet.
I think that is something that you will have to do. Okay.
Yeah.
See, I will, before taking the bull by the complete entire horn, I would, first see, let me see if I can do this. Okay. And maybe if I have problems, I will, there are, things that I'll have to do. Okay. So that is something that you will have to, that you'll have to do. Now, let me get to your particular issue. Okay. Let's defer encoding the property a little bit. Okay. Defer that for some time. What is the issue that you were trying to explain to me when I interrupted you? Okay. Can you explain?
Yeah. So Madhukar sir had basically explained how to verify an RNN using inductive invariance, right? So I was not able to extend that to an LSTM like this.
Yeah, no. Okay, what property? Okay, now let's get to this property. Okay, maybe we already discussed this, that through the invariant approach, you may not be able to come up with invariance for all kinds of properties. Okay, so now, okay, so if I understand you correctly, what you're saying is you don't know how to verify. You're looking at the most complex properties, right? This LSTM property. Now, suppose you had some cyclic property. Okay. Okay. So generally what you're saying is you don't know how to come up with an invariant to verify a particular these properties, a suitable inductive invariant, correct?
Yes, sir.
Yeah. Okay. So for that, let's take, okay, now Diganta, you take over. So I think I feel that there might be, I can see that there is some challenge, for all, for the most complex kind of properties. But let's see, there were some cyclic properties, etc. So that Diganta, that you had proposed, for which we had, at least I understood that for that, at least one should be able to come up with inductive invariance. Okay, so so why don't you refresh all of us with the kind of properties that you had proposed? So let's take the simplest of them and then see if the technical issue of proposing inductive invariant is there as it is pointed out.
Yeah. So I'm audible, right?
Yeah.
Yeah. Okay. So so we had like sort of I had given examples of three properties here. The first one is this coating property. So this is like a property where we sort of use this fact whether this LSTM coats are given data set or not as a measure of whether it has been overfit or not on the data. So so this property is basically we're going to take a string from the data set and see if like given any starting point, is it possible that the LSTM is going to generate this string as the maximum probability output, this exact string? And if you make this string fairly long, then we should, hope that in a normal LSTM, after a certain length, you won't like generate this one string as the maximum probability output, right? So the idea is then becomes like if you're still generating this one string from the dataset as the maximum probability output, then your LSTM.
Yeah, but what is the, let's look at the property that has to be verified here. So given a string, okay, of length, say n, where n is some length parameter, okay.
Yeah.
What is it that we have to verify for every case? So this property is true if it does not produce identical string for any sub prefix of the string, correct?
Yeah. So even if we don't go in terms of prefix, we can start from just from the latent state. So we have some string of length, say n, and we also have say some latent state, initial latent state given by h comma c, right? So what we are asking is, so if we have
even before expressing in terms of latency, just say what the property that is just now stated, for an arbitrary n. Forget about HC, okay?
Okay.
That is a way, means to produce, okay? Let's suppose now I have this RNN, okay? And I have a string of length 5, say, to be very specific, okay? And now I want to check, I have to run through, okay, this string. So I'll have to do 5 iterations, correct?
Yeah, so we'll have 5 copies of this. So there's something coming in here.
No. What he's talking is we could unwind it, have 5 copies of it, okay, and then do it, okay?
Yeah.
Or, I mean, first, even before you do it, what does it mean for this string to to pass that property? So the property is when I pass this 5 through an RNN, okay?
Yeah, so instead of thinking of it
that it comes should not be identical to this string. Yes, correct?
Yeah, okay. So that would be one way to look at it. I mean, another equivalent way to state it would be that the RNN does not generate this string as the maximum probability output.
So, that is more like it. Okay. Yeah. So, the maximal means what? Okay. So if I were to state this, okay, so that is one thing is the output that it produces. See, the output itself has to be a string. I mean, you will have to run this for a certain number of times, right?
So in this case, 5 times, and we'll get a string of length 5. Or rather, more specifically, we'll get some probability distribution on a string of length 5.
Yeah.
And then the maximum probability should not be of this particular
string. But it won't be the same string, right? It'll be shifted by 1, if I'm not wrong. Because
yeah, sure. So I mean, I'm just taking that implicitly into account in some sense.
Okay. Yeah. No, but you'll basically only be checking on 4 because you won't know what is the next.
Yeah, so that's why I was talking in terms of the latent state, is because we won't actually. So if this string is say, for example, say HELLO, right? So I'm not asking whether it generates ELLO after seeing H. I mean, that might be something reasonable that it does. I am asking like, is it possible? Is there any sort of hidden state, right? Latent state that it has already seen, from which it will generate hello world, or let's say, and some other thing, something fairly long. Will it generate this exact string? Like, is there anything here from which it will generate this exact thing? Right?
Oh, wait, no, I'm confused. Can you repeat
I'm
again?
also confused. I don't know what
I-
you mean by that. So, I mean, I can understand that the quoting property is if I feed this, it should not generate the same thing. Because, if there's any hidden state from which, if you do one more step, it'll generate hello world. What are you-
No. Not one more state. So I'm asking, is any hidden state from which it will generate this entire hello world string? So essentially, when we are, in some sense, when we're feeding it, say H, and we are getting E. So remember that not only is there this H coming in, there's also some hidden state that is coming in from the previous iteration, right? So when we start the LSTM, we have some fixed H0, C0 that we start with. Usually when we start a loop.
Okay.
Right. But so I think I think I've set these to 0 in my code, if I remember correctly.
Yeah, you have.
Yeah.
Yes.
So we are starting with H0 and C0.
So what is this hidden state? The hidden state will have, if I'm testing it on 5, it'll have 4, a string of length 4.
No. This hidden state is just some vector. This is the memory neurons in some sense.
Yeah, I know, but that entirely depends on what your structure is, no? So this question is even.
No, the memory neuron's length or size depends on the structure, but in some sense, the memory neuron is trying to encode what it has seen before.
Yeah, so if I want to test it for 5, then it would have seen 4, no? Before.
Yes. Yeah, but like if you want to test it for 5, then okay, so it makes sense to say that we have seen 4 only if you're generating this last thing, right? So essentially, say if we are generating this hello and say that it has already seen this part before, right? Then the memory is going to, so when we're generating this last O, then the memory is going to somehow encode the fact that it has seen HELL before, and then it's going to decide based on that to generate an O.
Yeah, so wait, so can I just explain what I thought it was? So so basically, given any H comma C, so given any latent state, if you are given the input string as hello, then first when you are given H with max probability, it should output E, like if it outputs E, and given HE with max probability, if it outputs L, then given HEL with max probability, if it outputs again L and O, then only in this case does it actually overfit.
Yeah. So I'm saying that so that is one way to maybe state this, but what I was saying is that instead of having this extra assumption that you're going to feed in H in the beginning, right? What I'm saying is you can also just drop that assumption. Because I mean, so having this extra assumption that you're going to feed in H is in some sense equivalent to just putting this H into your
connection between this property and the original property is unclear. Okay, that is what is confusing them. Okay, so what does it mean to say if there exists a pre-state? Okay, so at least and then its relationship to inductive invariant is even less clear. Okay, if you put it like that. Okay, so maybe the condition. I mean, for example, if I'm if I'm getting the next character to be O, and if I've already seen HELL, then my property will be violated. So there exists something, a 4-length character, which when, which is that what you call as the hidden state, okay, for which it gets violated. Is that what you're, saying when you say, does there exist some condition for the hidden state, which when, after that, when you see O, it will violate the property?
Yeah, so I'm saying essentially something like that, but except I'm not asking it in terms of just a single O, but I'm saying that it should be for a large enough string. So what I want to encode in some sense is there some arbitrary prefix that comes even before the hello world? Like say the LSTM has seen something before the hello world. Is there some string there?
What you're stating now is a completely different property. Okay.
Yeah.
Not
So I don't.
as a quote property.
Yeah. So I think so I think at least what Harsh is saying is the quote property. I'm claiming that it is in some sense equivalent to what I'm saying right
Why?
now.
How?
Yeah.
You guys,
so-
you guys understand? I don't. Okay. So, or
I'll
what you
just-
have to do is you will have to say what you have to put some condition on the hidden state. Okay, which is what I'm trying to say, and that could be the invariant. Okay. For example, if the quote property is preserved for up to 4, up to 3, up to, for every length of character, I mean, a string up to 4, then you can check if it may, what is the consequence of adding it, extending it by 1, okay? I mean, only then the connection to inductive invariant comes. Otherwise, what are you saying, okay? So what I'm saying is that the condition for, I mean, what Harsh or whoever that asked that question, there was one question of how you formulate it. There's this other question of what use is inductive invariant, okay? Here.
Yeah. So, okay. So maybe I should just let me talk a little bit about.
Yeah, but maybe what you should say is what your state. Just state what you're, stating, because it's not clear what.
Yeah, sure. So I think
what is the property that you're stating is, because if I look the RNN as a black box, then this hidden state. So RNN is getting as an input the thing from the previous thing, correct?
Yeah. So I mean, this star here is basically it's basically some hidden state that is coming from, or that has been.
What is the structure of that? What is the data type of that hidden state?
So that is just a vector. So this is a vector. This is this H comma C thing.
So, so in our case, it's both 400 comma 400 length, right? Because
so, or some, like, basically, so you can concatenate it and think of that as an entire vector, right? So essentially, it's just a bunch of real numbers.
Yeah, but that is true. That may be a bunch of real numbers, but they'll be interpreted as some string, no?
No. It's just a bunch of real numbers. It is what the RNN has internally stored as whatever context it has.
How can you even come up with some condition on that gibberish, okay, which is HC, and related to your property of quotedness?
Yes, sir, that is the doubt I had. Like I was not able to
because
get
I don't
around
even
this.
see that connection at all. Because HC is, as far as I'm concerned, gibberish, okay? Because I don't know what HC, the internal state, you'll have to map it to some input that it has already seen. Like saying, okay, if my whether that memory that it is having it is something that either satisfies, you'll have to map it to the input that you've already seen. Otherwise, how can you verify this quote property?
Yeah, so essentially, then in some sense, the problem is basically something like this. So initially we have no condition on HNC. So HNC can be whatever. And then we are asking that, okay, is it possible that
So, okay, but let's for a moment forget about inductive invariant and so on. What is it that you're asking as a property to be verified? Is there a condition on this structure HC such that what?
So is there,
when I read one more input with this?
Is there any HNC such that if we keep generating these characters, right?
What do you mean generating? So which means I'm reading more and more inputs, correct?
Yeah, so you're reading more and more inputs. So you're reading some input here.
No. Show that for this box where you have star.
Yeah. I'm drawing it like that. So you're reading some input here.
Yeah.
Then you'll end up outputting H. And then, you're reading this H is going to get passed here now. This can again be star. So what Harsh was saying was, or I don't think it was, I don't remember if it was Harsh, correct me if I'm wrong, but basically what they were saying was just starting at this point. So this was their first iteration. All I said was that, okay, yeah, sure, you can also start here. But I think that is not really...
No, so you can start there if you look at, like in the LSTM picture, the final DNN. So is that what you're doing? So the final DNN of which converts H to a character. So this DNN. So if you apply that to the arbitrary H, is that the input? So then you can give that input basically. Because you have to give the LSTM you have to give the LSTM an input as well as H, C, right? For it to first give an output. So are you saying like you arbitrarily pick an H, C, then you apply that final DNN on this edge to see what the character is, and then give this character and H, C to give an output, and then see if it gives the same. So basically you're saying for any H, C, does it give the same output?
Yeah, exactly. So essentially that's what I'm asking. So for any
but then it is not even clear. So because after 1, 2, 3, or how long are you asking?
Yeah, so that is again as you said fixed here as n, or in our case as 5. So here we want just we have picked a string. All we are asking is that for any H, C, will it produce this particular string? And 5 is a very small number for this.
Means what? Hello world?
Yeah. In our case, let's say hello world.
If you start from some arbitrary history,
right?
And if I now read 5 more inputs,
right? And remember that once we fix the history,
let me finish.
Yeah, sorry. Yeah.
Okay? So for any arbitrary memory, so which means it is actually the internal state which is coming as an additional input. Okay.
Yeah.
And if I read a certain number of string characters, then will I end up producing what?
Will I end up producing hello world as the maximum probability output?
Yeah, but you will obviously do because why should that be equivalent to the original property? Because because H, C could be whatever, no?
Yeah, so that whatever in some sense is encoding whatever the network has already generated. So instead of 5, if I give if the string is of length 50, then maybe it'll start to, so it'll sound much more sane in some sense. But the idea is this: if a network was generating some large amount of text and it has generated some text, then it should not end up quoting suddenly for 50 more characters. It should not end up quoting the data set and then just continue to generate text again.
So what do you expect here? So if the memory is, say, let's suppose I check it for one H, okay?
So
this will always fail, no?
Yeah, so for very small n, this will always fail, because like if you check for 1, so if your string is just H, then all you're asking is, does the network ever produce H as the maximum probability output? And of course, it sometimes gives H as a character, right? So so in that sense, yeah.
Well, I don't know if indeed what it has already seen, which is what is remembered in HC, could be something which, when extended by H, makes sense. It would give something else, no?
Yeah, it could, if what it had seen when it is or what it has encoded in terms of HC, if you extend it that by H and it makes sense, then yes, it will fail, right? But then if you slowly start replacing this singular character H by larger and larger strings, then at least the probability of it outputting this exact string should go to 0, right?
Wait, so what
Because-
so let me just get this clarified. So
Yeah.
you're saying basically that you want to check whether there exists some h comma c
Hmm.
such that so h comma c is basically a thing saying what is the past history, right? So for given some exact past history,
Hmm.
does it return the same thing every time? That's what you're saying, right? So
Does it return something that it has some very large part of the input data set? Exactly.
part of the input data set. So how do you like?
What is the input here?
Yeah,
Hello?
what is the input data
No,
set?
no, as in input. Sorry, I mean training data set. So I should not. Yeah, part of the training data set. Exactly. So remember that the way we are saying that this string we have picked from our training data set, right?
Okay.
So what I'm saying is that given some arbitrary history, does it end up generating a large part of the training data set verbatim as its output? Because that should
okay.
not
So
happen.
then in that case, you'll have to check basically for length 50, you'll have to go through all the possibilities in that input data set and then check.
Yeah, maybe that, I don't know how big the input data set is.
Because
Yeah, so the input data set is around 20 KB, but I mean, I think if you can check it for one string, then it just linearly increases for the input data set. I don't think that would be
No, but you have to
so
do
bad,
it
yeah.
every datum in the training data set. No?
okay, wait. So just to like
Mhm.
so that we can work better with an example. Suppose the thing was I don't know what's a good extension. Hi, hello world, something. Okay. So then in that case, if this was your whole data set, suppose,
Right.
now you're saying that basically you take a length and suppose here you say you take length as 5 instead of 50. So now you need to check that for any h comma c is there, or is it going to output suppose HIHEL or IHELL or HELLO or ELLOW? Is that what you're saying basically?
Yeah, basically that is what I'm saying.
So you'll have to keep going through in five character segments through the whole data set and checking whether it outputs the same thing again. So for any h comma c, does it always output does it code that thing exactly?
Yeah.
For up to a certain length. Okay,
Up
this
to,
one
yeah.
You can only check this and okay, this is just for one particular input. Okay.
Yeah, so this will all be respect to the particular data set that we have trained.
Yeah,
it
so this is
against.
only based on, so there is no input here. So this is just, you're just checking whether it quotes any 5 length segment from the data set exactly.
Yeah.
So it would be any of this, right? So even if it just quoted HEL also, it would be wrong.
Yeah. So that is basically the framework.
Yeah, but how do you do
Okay.
that without enumerating over every single element in the training data set?
I think that you'll have to do, right? You'll have to enumerate.
Yeah,
but I think his point was that it won't be that expensive.
Why?
Because
first of all, there must be a better way. See, when you do formal verification, even you do for all inputs and things like that. But here, if you're insisting that you have to do for every, doing it for arbitrary input is easier to state than saying, oh, for every input in this set, you check. That can only be checked by saying, oh, if it is this input, check. If it is that input, check for every input in that set. Is that what you want them to do?
Yeah, I think for this particular problem, I don't think we can do anything else. And
that doesn't make sense. Okay, I think given why do you want to check only for the
Hello?
No. I'm thinking that this is not a very interesting property. I mean, why do you want to check? Yeah, but this is almost like running the thing for everything. That's all.
Yeah. So I mean,
although you are quantifying the memory part. Okay?
Yeah. And
That part you're doing it.
That is why I think like this is not exactly running this over this.
That I understand.
Yeah. So in fact, this of all the three properties, I sort of
No,
meant
but maybe,
for this to
maybe
be
what might be interesting is to actually check for why do you want to do it only for the training data? I mean, you don't want it to quote for any input, no? Even if it is trained on a particular data, why do you want to quote for anything else?
No, I think the point was that you don't want your LSTM to memorize the training data. So that is what. That is what.
Plus, you can always avoid problems with copyright. Like if you're training in the real world and your training data is copyrighted, and you can show that it never quotes from the training data set.
Yeah.
You have
So
less of a
maybe
legal
then you
problem.
will have to iterate over all the thing. Okay, so let's suppose that you iterate over that. Okay, because that's pretty much you have to iterate over that because you want it to be checked on every input in a particular set. Okay, so that part is is not exploiting the power of SMT. So be that as it may, yeah, you could. Yeah, but okay, so I guess you can then, in another way, you can exploit it if it is. I mean, I was wondering if, and I mean, suppose you, for any particular thing, you will have to check that for, yeah, but I thought that, for even for this hi, hello world, if you start with the memory, like whatever the initial state is, why do you want to do it for an arbitrary thing?
Yeah, because see, if say our the string that we are looking for, that the bad code that we want to eliminate is this, then we want to eliminate this from being quoted at the beginning of the text that we're generating with the LSTM, or after we have generated some amount of text, right? So the difference between these two situations is the difference in the memory.
So when you do this, there is a blank. Okay, you're at a word boundary. That's the assumption that you're making. No?
Okay, yeah. I mean, we can say that we are at a word boundary, but I mean, in general, it doesn't need to be in a word boundary. What we're saying is,
but then see, the reason that you have to have some such assumption is because then maybe if H itself is tagged, I mean, concatenated without a blank there, then what does it mean? Okay, it's not even hi, hello world, no? If HC, that what it has seen is something like A or something like that, okay?
Yeah, so if it is seen just A, then in any case, the LSTM should not fill it with hello, right? So what use is checking for arbitrary history? I don't understand. No, I mean, if you want to say that, if you want to encode that we are at a word boundary in terms of H and C, so if it is correct with respect to that, it should also be correct with respect to arbitrary things. So I just said arbitrary because I thought that would be an easy enough over approximation for whatever other condition you can imagine. Like as in, all I'm saying over here is there is some blank here. I'm asking, is there something, and then we are quoting hello. Then this something can be anything, right? You can say that, okay, it can be something that does not end with a word boundary.
So this is something that we think, okay, so, okay, but then in checking this, if it violates, okay, if it violates for even before, I mean, if it ends up giving the same thing all the way up to WOR, up to hello, and then replaces it with something else, then you're okay. Huh?
Yeah. Like say, instead of So if our string is hello world, then instead of hello world, it could go like hello Bob, or even hello Will, you know.
Okay, so at least what they can do is in this verification, if as long as the condition, if it violates prematurely, then they might as well quit, instead of going all the way till the end.
For the data set iteration, yeah. Yeah, that is definitely the case.
Yeah,
and I mean,
but the reason that we should think of some properties that are more interesting is, let's think of properties where they can actually use. I mean, in this verification, is there use for inductive invariant? Because
no, yeah. So I actually intended this particular property to be a fairly easy and like direct property to check, just in case sort of everything else failed.
Direct? What do you mean by direct? Without using inductive invariant, you're saying?
Yeah, because over here we're only quantifying over one thing, and I think.
But then you have to let it run for, if it's.
Oh wait, how are we quantifying only over one thing? This is a 50 length thing, right? So how?
Yeah, it's a 50 length thing.
You have to unroll 50.
You have to unroll it 50 times, no?
Yeah, but even if you unroll it 50 times, the only in some sense the only variables here is the initial HC, right? Because after that everything else is in some sense getting fixed.
So here unrolling shouldn't be that big a problem, is
it? I think that, I mean, it might turn out to be not be the case.
Still, if you unroll 50 times, why will it? Your network will still be 50 times bigger than the original one. Why will it be any easier?
Yeah, like you'll have to run it through. I mean, you have to run it through all. Okay, wait. So for some h comma c, you'll have to check that this, like in your SMT solver, you'll have to put like for some HC given in some bounds, obviously. Does it for each 50 length part of the data set, does it output the same thing? Right? Like, does it output the, yeah, okay. I'm a little bit confused. But
no, that is the exactly thing. I mean, so you fix some HC, right? And then first of all, this should be the thing, like this character should correspond to the DNN output of that H, right?
Yeah.
And then you fix some strings. So you fix say hello. So you have passed in the HELL of that one over there, right?
Okay.
So that is your input here, and then you're asking whether HELLO is your maximum probability output.
Okay, so let's do one thing. Yeah. So how are you? So no. Sorry, I interrupted. So, but you still have to this. I mean, I can't see any way in which an inductive invariant can be exploited here.
Yeah.
So here when you're unrolling, you'll have to. I mean, yeah, you'll have to unroll in this case because, like, even when your RNN code to encode that, to encode the LSTM, rather, you'll have to basically give it the same, like, introduce new variables for each different time step. So you'll have basically, if it's a 400, it's not 400, it's much more. But suppose if it was just 400 neurons, then you'll have to give it for like 400 some 50 times, and then you'll have to check whether this network can then this is your network. Basically, you'll have to model it in this way. So the modeling will be actually very huge, right? So in this case, because you'll have to model it 50 times.
Yeah. So if we can, like, so one way to use inductive invariance in this case would be that if we can find some condition on the H and C coming out over here, given that it has seen something and outputted H, right? And then does that give us an E and C, and then a condition here, and give us an L and a condition here, and so on?
Yeah. So the thing is, even in the RNN, like I went through the paper that Madhukar sir like went through. So even in that paper also, they were doing it for basically they were doing it for RNN, and they were only doing it for one input and one. So where one memory unit is only connected to one neuron. So in this case, our HNC is connected to all the so each part of H and C are connected to all neurons of the forget gate, the input gate. So 400 by 400. And like in the RNN, it was just so, and the input will be of length 58. In the RNN thing, the input was only one. And you have to basically so in the RNN paper, the assumption was that your inductive invariant is linear in some form, and then you kind of search through that thing and try to find the invariant.
Right. So they were taking intervals, in fact, right?
Yeah. So they were taking intervals. So no, I mean, I was just thinking, like, I don't know how to get this to an LSTM, because it will be very huge to do that. I think that itself is very
unless you could do something. See, the one thing is, well, that's why I'm saying, okay, there could be a thing, and there's something that we need to think through before we can assign it. Okay, so you see, if you're proving it for an arbitrary H star C, so if there are several, say this hi hello world, hi hello Bob, hi hello Susan, etc., this thing, then if I don't know, I mean, if you've already proven for hi hello that it is going to give different for an arbitrary thing, after that, since you've already proved, if you already proved that for an arbitrary thing with starting with an arbitrary memory, if it sees world, it gives different, then it would also should be true for hi, even for the prefix with hi hello, correct?
Yeah, that makes sense. So essentially, if we have say figured out that starting from arbitrary thing, it never produces world, then it cannot ever produce hi hello world.
Correct. Yes.
Yeah. Or if we have figured out some condition here, or extending that a little bit, if we have figured out some condition here that prevents it from ever producing world, then all we have to do is show that condition is going to end up being satisfied if we go through hi hello. Yeah, so I think that's also something that we can do. Yeah. But again, I think like in terms of figuring out what these conditions could be, I don't know if there is anything better that we can try right now than the interval search one that they had, right?
Okay, so let's think about this a little bit more. Okay, so you had a cyclic property, no? So let's think of some property that they could be working on in which it is, where we can exploit inductive invariant. Okay, so to see if there is one.
Yeah. So do you want me to
at least be productively engaged in verifying that property while we clean up the rest of the properties, okay, on our own before we assign them. Yeah. So because we are finding. So there was, what else was there? So what do you mean by getting stuck in loops?
Yeah. So this property was this thing where we want to check whether there is some. So we have again fixed some length n. And we want to check whether the LSTM ever reaches a situation like this. So there is some H comma C here, and it sees again, this H is going to determine what input it's going to see in the next one, right? So this, you can think of this H comma C as being the entire encoding of the LSTM state. And then here it produces something, here again it produces something, here again it produces something. And finally, after say 4 things, it comes back to the same H comma C. So does it like, is there some H comma C, is there any h comma c for which it enters a cycle like this, because if it enters a cycle, that means that,
No, what do you mean by cycle?
because I am calling this a cycle because the state that you're starting with, h comma c, is the same state that you're ending with at the end.
If it enters, then if you fed the same sequence of inputs, you would get the same thing, correct?
Yeah. And since in our case we're generating text and the sequence is just dependent, like the inputs over here are just fixed by whatever we saw before, right? Which was again fixed by the h because of the structure of the LSTM. So in some sense, if we end up with the same h comma c by starting from the same h comma c, then we are guaranteed that
Just a slight diversion.
Mhm.
So what does HC, I mean, I asked this question, if in some ways HC is an encoding of what has been seen before, okay?
Yeah.
So both this H and C are numbers, real numbers.
So both of them are some vectors. So h and c,
Vectors denoting what? H denotes the previous character that it saw, or what?
yeah. So h in some sense denotes, so h then passed through a neural network layer gives us the previous character that we have seen. So h is the hidden state, and in some sense it denotes the previous output of the LSTM.
Okay.
And
C?
C is the memory cell. So that is where we forget things, write new things, and so on.
Yeah, but what do you remember there? That H
So-
gets put in C, no? In each thing.
Yeah. So parts of h gets parts of the previous h gets put into the C.
Put into the C. So really, C is the history.
Yeah, and h in some sense is the output. So we can think of it like that. So another way to think of it,
Which is a transformation over the input, and H is a function of the input and the previous C. Correct.
yeah. So if we go back to the diagram, then this is the h, right? And this is, as you can see, it's a function of the previous C and the input. And I mean, of also the previous h, but the key thing is that the previous h cannot ever pass through to the new h unchanged. So h in some sense is the function of the immediate previous thing and the history.
Yeah,
So-
and in this case, xt you can get from ht minus 1, right? I mean,
Yeah,
if you're
If you're fixed ht minus 1 and ct minus 1, if this is your two variables,
Hey,
then
if I were to think of proposing some inductive invariant, okay, this is what I would do. Is there something, and I don't know, I mean, go back, go back to that picture, yeah?
okay, yeah.
Is there some equilibrium, okay? Does that, for all, if this HC kind of stays the same within certain bounds, okay? Always stays the same within bounds. Okay, for arbitrary inputs and for thing, okay? Then, or even for a particular something, that is the kind of thing that you will have to exploit maybe to prove properties for arbitrary length. Okay, will is there? Yeah, this needs to be thing. I think we should have thought about this a little bit more. Okay, so let's go back to your thing. Okay, so now H and C are there. So somehow there must be something. What can be an invariant in this thing? I mean, the only thing I'm saying is, if you keep feeding the same sequence of inputs through it, okay, if that HC ends up being the same, okay, then throughout the thing, then it's it is almost sure that it will produce the same output. Okay.
Yeah. So
therefore, given that you don't want that thing to happen, or even if that HC for the same input, if I keep feeding the same input, and if I get HC to be very, very close to each other, okay, the likelihood that it will quote it is very high, okay?
Or the likelihood that it will end up repeating itself ad
Yes.
infinitum. Yeah, it's
Yes.
very high.
Yeah,
Exactly.
so instead of saying it will be the exact same, you can say it will be close.
Yeah.
It will
Yeah.
be close. It will
Yeah,
be
we can
close,
fix
okay?
some epsilon and we can say that it will be epsilon close, let's say.
Yeah, it is something, yes. So if you want it to be different, then you want the HC to be not within that limit. Huh?
Yeah. So just
That is the kind of thing that you will have to exploit. Okay, I can see.
yeah. I think maybe that is the thing that we are. So essentially, what Sir, you were saying, if we had fixed n to be 1, then what you were saying is basically directly what we want, right? Because then this is the situation that we are asking for, right?
Yeah.
Yeah. So this is the situation where that we want to check for. So if this situation happens, then for any n greater than 1 as well, we have a problem. Is basically
Exactly right. Yes.
Yeah.
And
Yeah.
this is extended to for some arbitrary length. Okay. For some arbitrary length, if it once again is identical or it is so close to each other, then your outputs is likely to be close to each other too.
Yeah. So for arbitrary n that you're saying, right? So some picture like this.
Yeah.
Yeah. So this is basically what this problem is. So given some n, checking if the initial H and C and the final H and C are very close. to each
Then why can't you express it as that for arbitrary inputs or for every training inputs? I mean, you could check it for both things. That will that HC tolerance on HC will be different, okay? Will not be too close, but it will be different, okay, by a certain tolerance. Is that worth checking then?
So can you just explain what exactly you're saying? So you're saying
of what HC? Okay, if the HC is too close, then the chance that the output will get quoted is high.
Yeah, so not quoted but repeated. So this is the second property that we are.
The second property.
Yeah. So we're not talking about quoting here.
Well, can you not? Okay, I'm also thinking that something like this can be, variation on this can be done for the quoting also, is what I feel. But here that is certainly the case. No? Therefore, you can exploit that, improving for arbitrary length. Therefore,
so exploiting. So for example, if your query is for length 4, which is what we have drawn here, right? So then you're saying that what we are going to exploit is that at this point it should also not be very close to HC. So that's the first thing that we can check.
Every time it should not be. It should not be very close. Yes.
Yeah. And then this one should also not be very close to whatever either this
that should
one
be
was.
preserved as an invariant. Okay. That it should not be very close means it has to be, the difference has to be greater than a certain amount. Okay.
Yeah, exactly. And if our
that
final
has to be true for all I less than or equal to whatever that thing, because we can assume that this invariant will have an I, okay, which is the iteration counter. Okay. So as long as I is less than or equal to that amount, like in the paper that Madhukar discussed, that they used in all the invariants, the counter was there as well. Okay. And as long as I is less than or equal to n-1, okay, that difference between the HC, the input HC and the output HC.
Yeah, should be some linear thing based on the I. Yeah. So essentially, this one. So let's call this H okay. So let's call this H prime C prime. Then it would be something like H prime minus H should be less than epsilon by n. Something like that, right?
Correct. Yes.
Yeah. Exactly. So that is why I think invariance can be useful.
Yeah. Now, once you prove that property, the chances that you won't get cyclic loops, okay, should be, you will not get cyclic loops, should be high. Now, it may not be perfectly, I don't know if it will exactly be true or not. Okay?
No, yeah. So if we can, if this is an invariant, then we'll end up with it being exactly true. So I think we can look for invariance of this form, right? So
this time, then you can actually check. I mean, if indeed it preserves this property, then you can check if it is, I mean, if it does not, then what do you do? I mean, you could keep on relaxing the tolerance. I mean, or tightening the tolerance or relaxing the tolerance.
So yeah, we can relax the tolerance and see at what point it begins to like satisfy. So for example, if we cannot prove this, then the question is it because the invariant is weak, or is it because it actually give for this particular value of tolerance, the network actually is cyclic?
Yeah. Okay. So that's one. Okay. So this is one. So, okay. Now I
think, yeah.
Go ahead. Does someone have any questions here?
No, I was just saying that I think this could be like something interesting in terms of the properties.
Yeah.
Yeah.
Now, I feel like maybe a little bit of a tweak on this can be used in quoting also. Okay. Here's my idea. The quoting idea is that, so let's suppose, I mean, I'm saying quoting is quote if their two are identical, correct? If it produces the same thing.
Yeah. So
yeah, but let's suppose that you say, oh, I allow for up to a certain difference. Okay, the difference has to be greater than, certain amount. Suppose you make a measure. Okay.
Okay. Yeah. So
you make a measure that it has to be, that I want that to be different. Okay. Then I don't know how you will actually check this. Okay. Yeah, I don't know what the yeah, I mean, when you think of invariance, what you're trying to do is to how the question, guys, that the question that you will have to ask is there some condition on the invariant condition on the history that I can make up that will, which when preserved will help me to prove this property for an arbitrary length. Okay, for using enumeration, you can prove it, as we are already, Diganta demonstrated, right? Okay, correct?
Hello?
Yeah. I mean, are the rest of the people here?
Yeah.
So, for a particular word, for a particular length, you know how to prove the preservation of the quotation property. Is that are we on the same page on that?
No, I'm not sure can you repeat what you said? Like,
for a particular string, like hi, hello word of particular length.
Okay.
You know how to check that the quotation property is not violated for arbitrary history.
If you're allowed to unroll it, then yeah.
Yeah, that part, okay, and you can extend it to, if you're allowed to unroll it for as many times as you want, depending upon your input, you know how to prove, okay? So the question that I'm saying is, I mean, if you want to see if there is an inductive invariant that can help you, where it can help in these cases is, if I can come up with some invariant condition that when preserved, I'll be able to use it for checking this property for arbitrary length without unrolling, okay? That is, if it is preserved, if that invariant property is preserved up to 1 through n, okay, then it'll then so for every 1 through up to n it is preserved, then it will the quotation property will not get violated for n plus 1. Okay.
So
I
I have
do-
one doubt in all of this, that basically, so when you look at loop invariants and even in that RNN paper, the loop is the same, right? But here that's not the case, because we are not exactly looping the same thing again, right? Because we have giving it different input every time, and more than different input, a different memory.
Inputs can be different in loop invariant also.
But no, what I'm like, okay, I have to think about it.
Yeah, I think in terms of this and loop invariance, the structure is sort of the same, right? Because
Yeah, but I
think
think
about
what he's saying probably is that as you unroll it, I mean but see, because that's why we are applying this condition on the history, huh? Because every time that HC will be something that is that preserves the invariant. Okay. Yeah.
So in this case, you're looking at HC and X at each point as an input.
Correct. Yes.
or I think another way to look at it is that HC are your variables that or the state that you're keeping from one iteration to the next, right? Because from the H you'll also get your next input, and HC is also getting carried over to the next iteration. So does that make sense?
No, can you repeat once again?
So I'm basically saying that if this is your loop, so like while whatever and you're doing here, H and C are the variables that you have that you're carrying all throughout the loop. Because what you're doing is essentially is, you can think of it this way, that at the beginning you're using the H of the previous one to calculate X, right?
Okay.
I got it. Understood.
Yeah.
458 now. Okay. So I don't know if you guys have constraints.
Yeah. I think it's 450.
Yeah, I think I have some.
Yeah. So you have a class.
Yeah.
So I think what you do is
Quantum.
to at least for the why don't you guys start working on the cyclic property? Okay. So we will, Diganta, the rest of us, Diganta, Madhukar and I, we will think through the other properties and, come up with some proposals for you, okay? And then, we will continue this discussion on Wednesday, yeah?
Okay, sir.
Okay, sir. I'll also try to model the
Yes, I
RNN
think-
in that time,
yeah.
or the LSTM in that time.
Correct. Yes, go ahead, yeah? Was there a question?
No, sir. Sounds good.
Yeah, so what you can do is first do some unrolling and then verify this property, okay, the cyclic property, okay, and then see what I can, something like this. What if it is within that, then there cannot be, okay. If the tolerance between H prime and H, if the difference is within a certain tolerance, then it cannot repeat something, okay?
Yes.
Yeah. So, and for the other two kinds of properties, we will brainstorm amongst us and then see if what it means to prove it without invariant. If there is even inductive invariant will be of help. If not, how do we go about doing it? Yeah. So we will give you some inputs that you can actually do. Yeah. Feedback.
Yeah. So I just want to say that if so I mean I'm out of time, but if there are some doubts about what the second property is and what you want to look at, I'm available later in this evening after
I think
about
so. Yeah,
7.
you can help
You
them
can
out. Okay.
you can like message me on WhatsApp or email or email any of us. Okay.
Yeah, but I'm hoping
And
that
I'm
by
available. Yeah.
today, by taking Diganta's help, you would, three of you would make some progress in actually checking some property, okay, that is related to the second kind of property. Yeah.
Yeah, sure.
Okay.
Yeah. So yeah, just send me a message. Yeah.
Yeah.